Okay, so for our warm-up, we looked at the slope field. For dy dx equals 1 over x as long as x is greater than 0. And we saw that if we were to graph a particular solution on that slope field, it looks like the natural log. Now, when we first started talking about the general power rule, we said that if we had the integral, indefinite integral x to the n dx, we could solve that by taking x to the n plus 1 over n plus 1. It's a plus c, but we had that n cannot be equal to negative 1. That's the only way that that general power rule will work, as long as n is not negative 1. And the reason for that we'll see now, and we will get a formal definition, Joseph, of the natural log. The definition, last year we just had to talk about the natural log in relationship to the fact that it was the inverse function of the natural exponential function. But the formal definition of the natural logarithmic function uses integrals. And the natural log of x is equal to, from 1 to x, 1 over t dt, but x must be positive. That is the definition of the natural log of x. Its domain is a set of all positive real numbers.
Is that indefinite greater than 0?
Yes, because x is greater than 0, the domain is all positive real numbers. All right, now if we were to graph the integrand, it would look something like this if this is 1. So if x is greater than 1, that means we're going to start right here if we think about the area, and it's going to go this way. So is that going to be a positive value, or is that going to be a negative value?
Positive.
It's going to be positive. The natural log of x is also positive. If x is greater than 1, the natural log of x is positive. Now, if we start at 1 and we go backwards, what does that do? Say our x is over here, and we start and we go back this way. Is that value if x is less than 1, if it's between 0 and 1? What about the natural log now? Is that going to be positive or negative? Now, if we start here and go left, what did we learn when we were finding area under the curve? If we start at a point and we go back to the left, are these positive or negative?
No, it's negative.
They're negative. So the natural log would be negative if x is between 0 and 1. And now you can see from a calculus perspective why that's so. We talked about this last year, but we can see from a calculus perspective why that's so. But we also know now what the graph of the natural log looks like, and hopefully this is the graph of the derivative that we've seen. The natural log of x, remember, is going to look like this. The domain is positive real numbers. The range is negative infinity to positive infinity.
Is this still natural log of x?
This is the natural log of x. This is the graph of 1 over t, the derivative of the natural log of x. All right, is this a continuous function?
Yes.
It is a continuous function because if the domain is just x is greater than 0, there's no breaks in the graph anywhere.
Okay.
What can you tell me about concavity?
Always concave down.
Always concave down. Okay, so just some things. We talked about those kinds of things last year. Last year when we looked at natural logs, we also talked about some properties of natural logs that we will use when we find derivatives. One of those was that the natural log of 1 is 0. We kind of did it by rewriting it in exponential form. The base is e, so e to the 0. Anything to the 0 is always 1. If we have the natural log of a times b, we could rewrite that as the natural log of a plus the natural log of b. If we have the natural log of a raised to the n power, that can be rewritten as n times the natural log of a. Or if we have the natural log of a divided by b, we can rewrite that as the natural log of a minus the natural log of b. The definition of the natural log of e is from 1 to e of 1 over t dt, and that is always equal to 1. So the natural log of e is always equal to 1. And we learned that last year, but here's a formal definition. But the natural log from 1 to e of 1 over t dt is 1. If we have, and you can see now, if we went from 1 to 1, the natural log of 1 would be 0, because if these two match, you get 0. So you can see by the definition why the natural log of 1 is 0. We did it a little bit differently last year, but now with the calculus definition, it makes some sense looking at it in another way, I hope, of the natural log. But for the derivative of the natural log, if u is a differentiable function of x, now first let's just look. The derivative of the natural log of x is 1 over x. Again, x has to be positive. If we take the derivative of the natural log of u, it's going to be u prime over u. U has to be positive. Okay, you say that's not bad.
No, it's horrible.
No, it's not. So let's just look at an example of what we're talking about. The derivative of the natural log of 2x. Okay, we said that's going to be u prime over u. What's u in this case, Michael?
2x?
So what's a derivative of 2x?
2.
So 2 over 2x. So the derivative, it simplifies to just 1 over x.
Oh, it's
So that was really not as bad as you thought it was going to be, was it?
pretty easy.
Yeah, yeah. I think these are some of the easier derivatives to take. If we wanted to take the derivative with respect to x of the natural log of x squared plus 1. Well, if it's u prime over u, what's u prime?
U prime would be 2x.
2x over x squared plus 1. So you've already learned the hard part, which is finding du. All right? Now, of course, if we're multiplying, we have to use a product rule. Okay, so we can't forget these rules that we've learned in the past. They don't disappear. They just keep showing back up over and over and over again. So if we use a product rule, it's the first term. What's the derivative of the natural log of x?
Wait, can you just take the natural log of x to the x? I mean, that'd be pretty complicated, but you could.
Yeah, I guess you could, but I don't think you'd want to.
It's 1
In
over
fact,
x.
if you had the natural log of x to the x, you would want to rewrite it this way so that you could take the derivative.
So it's 1 over x.
X times 1 over x plus the natural log of x, and the derivative of x is 1. So we simply get 1 plus the natural log of x.
But should it over?
Look at whoops, Okay, that's not what I wanted to do. Let me move this. Okay, I want the derivative of the natural log of x cubed. So here we have to use, what kind of rule?
Chain rule?
Chain rule. So derivative of the outer term times the derivative of the inner term, which is,
Natural log of x.
what's the derivative of the natural log of x?
1 over x.
1 over x. Okay. So notice, this is not the same as the natural log of x cubed.
Right.
It's the whole thing cubed. So it makes a difference in how we actually integrate that. Let's look at one where we might need to use those properties. William, the example he used, it's much easier to integrate. In fact, I wouldn't know how to integrate it without putting that x in the front, the one you asked me about. Okay, so let's look at the derivative with respect to x of the natural log of the square root of x squared minus 4. How could you rewrite that? In fact, let me just do this. Y equals, and we want to find the derivative.
You can make that as natural log of x squared minus 4 just to 1/2.
Okay, we could make it the natural log of x squared minus 4 to the 1/2.
Can we use substitution here?
No substitution. What do I do with that 1/2?
Put it in front of the natural.
Put it in front. So these two statements are the same. They mean the same thing. It's just going to be easier to take the derivative if I have it in this expanded form than if I left it the way it was. In fact, I'm not sure how you would do it if we left it the way it was. But now if we take the derivative, we're going to have 1/2. Now how do I take the derivative of the natural log of x squared minus 4?
It's 2x over x squared minus 4.
2x over x squared minus 4. And the 2's cancel. So we get x over x squared minus 4. That one doesn't look as friendly as some that we've seen, but I think that we can rewrite it so that it will be easier to work with. Multiplication means I do what with logarithms? If I've got factors multiplied together and
You add.
we add, so you can have the natural log of x plus twice the natural log of x squared plus 1. Now what do we do when we divide?
Subtract.
We subtract minus 1/2 the natural log of 2x cubed minus 1. Now that didn't take too long to do. But now we can find the derivative much easier. So if we find the derivative, we're going to get 1 over x plus twice. What's in the numerator, Oscar? 2x over x squared plus 1 minus 1/2. What goes in the numerator? 6x squared over 2x cubed minus 1. And the only thing we can do now, I'm not going to make you get a common denominator. 1 over x plus 4x over x squared plus 1 minus 3x squared over 2x cubed minus 1. Here we have another problem. We're going to take the derivative, and you know how to do it. You can take the derivative by using the quotient rule, but we can also take the derivative by taking the log of both sides. And when you need to do this, you'll usually be told, find the derivative by using logarithmic differentiation.
Using what?
Logarithmic differentiation.
Using, how do you spell it?
Like,
Oh, logarithmic.
Okay, so we can take the derivative the old way, or we can take the derivative using logarithmic differentiation. Notice I said x can't be 2. Doesn't matter what x is, as long as it's not 2, it's going to be positive. Because you square what's on top, and you're squaring the x on bottom and underneath the radical. So as long as x is not 2, it's positive. And we know if we're going to use a logarithm, we can't have the logarithm of 0. So as long as x is not 2, we can do logarithmic differentiation. So to start, you take the natural log of both sides. So we take the natural log of y equals the natural log of x minus 2 squared because sometimes it makes it easier to differentiate. This one we could do without it. It's doable, but it's easy to do it with logarithms, and sometimes you're just asked specifically to use logarithmic differentiation. Okay, I have seen that on the AP test. So, all right, so if we take the natural log, or we take the derivative of both sides, we're going to get y prime over y. Derivative of y over y. I probably should have expanded that first. Let me erase this and expand the right side first. So the natural log of y equals twice the natural log of x minus 2 minus 1/2 the natural log of x squared plus 1. Easy enough to expand it. Because now it's easy to take the derivative on the right side. So we're going to have y prime over y equals twice 1 over x minus 2. What?
Should the second one be to the 1/2 power?
There it is.
It's 1/2 minus 1, so it's negative 1/2 power.
No, that's when you subtracted, you took care of that.
Yeah, but it's.
Okay, we're going to have 1/2 of 2x over x squared plus 1. I skipped a step. Is that okay?
wait, so are we solving for what?
Common denominator over here, which is going to be x minus 2 times x squared plus 1. And when we cross multiply, we'll have 2x squared plus 2 minus x squared plus 2x. Did that all in my head? Is that okay?
Yes, ma'am.
So if we simplify, we still have y prime over y equals 2x squared minus x squared is x squared plus 2x plus 2 over x minus 2 times x squared plus 1. Now we can multiply both sides by y. And we know what y is if you look back at the original equation. Y prime is now equal to x minus 2 squared over x squared plus 1 to the 1/2 times x squared plus 2x plus 2 over x minus 2 times x squared plus 1. This cancels. And we have x squared plus 1 to the 1/2 times x squared plus 1. So we end up with x minus 2, x squared plus 2x plus 2 over x squared plus 1 to the 3/2. All right, we have a theorem. Normally when you see the natural log, or real often you'll see it with absolute value, because that has to always be positive. Okay, but when you're taking the derivative, we don't have to worry about the fact that it says absolute value. The derivative of the natural log of the absolute value of u is still just u prime over u. The reason we get the absolute value bars is to indicate that that value is always going to be greater than 0. But when we take the derivative, we can ignore the absolute value bars. So if I wanted to take, say that f of x equals the natural log of the cosine of x. Because cosine could be positive, it could be negative. Absolute value bars tell us we're taking the positive value. But if we take the derivative, what is the derivative of the cosine? Negative sine of x over cosine of x, which equals negative tangent of x. And we will see that again later in the next section. We haven't found all the derivatives of all of the trig functions yet, so or antiderivatives of all of them. So this will help us in the next section. All right, but notice when I took the derivative, I didn't have to worry about the absolute value bars anymore.